With this video, we start our path to understand what monads are and why we do need them inside Haskell programs. And in these videos, we will be using a lot the GACI shell in order to see how some specific type classes are implemented. So I'd suggest to you to do the same. Open your shell and go in GACI. And in order to understand monad, it would be a great idea to ask for information about the monad. And we see that in the monad type class definition, we do have a constraint which is the applicative. So it might be a good idea to first understand what applicative are, since as we also saw in the exercises of the previous video, when we see some constraints into a type class definition, it might be because we need those constraints in order to define the function that are used for that specific type class. Therefore, we should also ask for information about the applicative, since it's very likely that we'll need to use some applicative functions in order to implement the function needed for a monad. So if we ask for infos of the applicative, we also see that the functor type class is needed in order to define the applicative. And for this reason, we are going to start from the functor. And finally, we see that the functor does not require any other type class to be implemented. So we can start from here. And this is the definition of the functor type class. And if we take a closer look at the functor kind, we see that it is not just something that, given a generic type, returns a constraint, much like we do see as an example in the num type class. Instead, we see that a functor is kind of a higher order type, which, given a function that, given a type, returns an entirely new type, returns a constraint, and this means that this is a type class. And we know that usually these kind of kinds are used for containers. As an example, this is the exact kind of a list, or maybe, or the either with one value provided. And what is common between these types is that all of them are able to contain other values. We can have list of numbers, we can have optional values, and so on. So we must assume that functor is a type class for containers. Therefore, we can create instances of functor with containers. And from the definition, we also see that the minimal in order to have such an instance is the fmap. And the fmap function does have a type signature, which is typical of an higher order function. It takes a function as first argument and then an f of a, and we know that f must be a container. So here we have a container of a's, and fmap, when provided with these two arguments, returns a container of b's, which happens to be the return type of the first function. And if you look closer, this type signature should be familiar to some function that we already encountered. And in fact, it is very similar to the map type signature. The only difference with map is that map only works with lists. And from the moment that list can be valid instances for functors, well, actually, if we ask for information about the list type, we see that there is, in fact, already an instance for a functor. Therefore, we can assume that map is just a more specific implementation for the fmap function that all functors must have. In fact, what is common between functors is that, of course, they all have to be kind of containers, but on these containers, we should be able to apply functions to their values. That is what a functor is for. A functor is a generalization for a container on which we can apply function on. That's it. This is a functor. In fact, since fmap is a generalized version for the map function, well, of course, we know that maps do work with lists, but since lists are a specific instance of functor and fmap works with functors, we can also use fmap, and the result is the same, since of course is morally the same thing. But a cool thing about fmap is, of course, that it works with any kind of functor, and we saw before that maybes can be functors, and if we try to use fmap with, in this case, an instance of a maybe, well, we see that this fmap works just fine. In fact, we are applying this function to whatever is inside this maybe instance, and well, of course, the implementation varies from the container. In fact, we can see that if we provided a nothing as argument, this is a valid instance of maybe, but of course nothing does not really add any value, so it just returns nothing. But yeah, by now you should have a clear idea of what this fmap is supposed to do, and since this is the minimal function that we need, we should already have a clear idea of what a functor is for. And with this idea, we are going to see some of the utility functions that may turn really useful later in the course. Well, of course, let's start by this other function that is common with functors, and the type signature is something that, given a generic type, in fact, this A is not constrained by anything in this definition, and a container of another generic type returns the same container, since we are using the same name in this type signature, for the type of the first argument. And well, if the type signature was not clear, we can, as always, try this ourselves. And here I'm using just a number instance with this operator. And then we have to provide a value that is inside a container which implements the functor type class. We can try this with a maybe, and the type of the value inside this container doesn't really matter. It can be a number just like the first type, or it can be anything else such as a string. And from this expression we expect to get back well, this f in this specific expression stands for a maybe. Well, actually this is not a valid constructor, so let me fix this. So we expect back maybe of the type of the first argument, and the first argument here is a number. So by evaluating this expression, we get back a maybe, in this case, of course, a just of the first value. And if we ask for the type of this expression, we see that this is maybe a, where a is a number, and we started from a maybe string. There is a dual function for that, which is the same function with the arrow from the other side, and we can first ask for the type of this, but before doing that we need to import the definition. In any case, we can ask for this type, and we see that is very similar to this one, just with the argument flipped. So we can assume that this operator is doing the same thing of the one above, just with the argument flip, and we see that this is in fact the case. And if we didn't like the fmap notation, there is also another utility function, well, actually an utility operator. And as always, let's first ask the type of this operator, and we see that this type is exactly equal to the fmap type. It does change literally nothing. The only difference here is that this is defined by only using signs, and so we can assume that this is just an alias for fmap that can be used as an operator, and our assumption prevails to be right. So in this video we saw what functors are supposed to be, and the main takeaway here is that functors are containers that are able to apply functions to the values they contain, and they are able to do that by using the fmap function or the operator alias that we can use by importing the data.functor module. So with this idea of a functor, we are going to see what applicatives are, since we needed to know what a functor is in order to understand what an applicative is. So if you found this video useful, consider to subscribe to the channel. Remember that if you want to support the creation of this content, you can always go in the description below and you'll find a link that allows you to delegate your data to a Harmonic pool. In any case, I want to thank you for your time. Remember to stay decentralized and I will see you in another video. Bye bye.